All right, hopefully you've taken a second to think about what the concavity means in terms of snowfall, although I'll admit that's a pretty tough concept to connect. This is not typically a question that you would have to answer, even on an FRQ or in a college setting, so it's worth noting that it is a little bit hard to interpret what big F concave up and big F concave down mean in the context of the real life scenario, but I'll do my best to put it in words for those who are curious. If you're not very curious, honestly, it's not that important. So if you want to fast forward this part of the video to get down to the bottom and do question I with me, feel free to fast forward the next couple of moments where I'm going to do my best to do this explanation, but I don't want to confuse things. And since this is not an important idea, I don't want to run the risk of losing some of you who have made it this far, so bear with me. Now, in context, concavity doesn't have to do a whole lot with snow. Snow increasing, I can picture that. Snow decreasing, I can picture that. I can picture looking out my window and watching a pile of snow get bigger, and I can picture watching a pile of snow get smaller. But the words concave don't have a whole lot to do with our vocabulary of snow. Snow pile up, snow piles down, or melts down, I can see that. But concave, in what context would you ever use that word? So instead of thinking of concavity, in other words, instead of thinking of F double prime, what I actually want to do is think of F double prime as the derivative of F prime. Remember how F prime was when things are increasing or decreasing? F prime, in other words, is a rate of change. So if F prime is a rate of change, or big F prime is a rate of change, and I want to think of its derivative, the derivative of a derivative, that means I'm looking at where the rate of change is changing. In other words, I want to know when the rate of change is increasing or when the rate of change is decreasing. Again, that's a pretty abstract concept, but that, in essence, is what F double prime is measuring. F double prime is actually measuring when the rate of snowfall increases or the rate of snowfall decreases. So the answers to question H part 3 are as follows. Big F is concave up in these intervals, which means if big F is concave up, that means the second derivative is positive. That means the rate is increasing. The rate of snowfall, that's big F prime, is increasing. That's your next prime. So rate is your first prime. Increasing is your second prime. That's your double prime. From time 0 to time 1. From time 4 to time 5, and from time 5 to time 6. Ran out of space. But when you think about it, the rate of snowfall is how fast the snow is falling. So we're saying that that rate is increasing. It's speeding up from time 0 to time 1. I guess that makes sense. Look back at the snowfall. It was pretty quick. To go from 0 to 1 in that first hour of snowfall, yep, it sped up pretty fast. I got from 0 inches to 2 inches, went pretty quick. And then it sped up again from time 4 to time 5. Now, if you're looking at that going, whoa, 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 no it didn't speed up, that's the wrong word, you're right. I mischose that phrase there. Because from time 4 to time 5, the snow was melting, but a negative rate does make sense. It just means that it got more negative more quickly. The snow must have melted faster. So while we can't really say the snowfall sped up, we could say the rate of change definitely increased, which means the melting rate increased too. If I was getting smaller, that just means it was melting faster. And then if I look back, from time 5 to time 6, that means the melt rate turns around again. Now I'm going back up to positive snowfall, so the snowfall must have increased again. The rate and speed of the snowflakes coming down must have started accelerating again. Again, it's a hard concept to wrap your head around. The verbiage has to be so precise that it's really difficult to put this in terms of snowfall. And that's why I'm not going to make a big deal out of it, and I hope you'll just hear and appreciate the fact that this does have a connection to real life, but that you won't fixate on it too much, because it is a legitimately hard thought to process, and it's not something you should be expected to know. It's not something you should be able to duplicate on your own. This is something that you can appreciate, but not necessarily worry about duplicating. Appreciate, not duplicate, should be the mantra here. Now, if you wanted to interpret the concave down information, that's when the rate of snowfall, that's when the speed of the snow falling, if you want to think of it that way, is decreasing. So it's almost as if to say the snowfall is getting a little bit lighter. That instead of a big, gigantic blizzard's worth of snowfall, where the rate of snowfall is really increasing, it's coming down really hard, the rate of snowfall is decreasing. It's lightening up. I'm picturing the precipitation rate getting a bit smaller and smaller, so maybe it's turning into flurries and just a few little snowflakes. And that's happening from time 2 to time 4, and again from time 6 to time 7. So there's my second interpretation there. And I can go back to the table to make sense of it. From time 2 to time 4, we're saying we have some little flurries going on. Well, that kind of makes sense, because snowfall was definitely slowing down when I hit my peak, and then after the peak was hardly snowing, because remember, that's where the peak, the rate of change is 0, so it had to kind of slowly pick back up again. That makes sense. And then from time 6 to time 7, that was another situation where we were hitting a peak, or in this case a valley. This was a possible low point. So it was slowing down because the graph was turning around. And that does harken back to the graph that we made. That the points at which the graph is kind of accelerating the most are the places from 0 to 1. Really takes off in that first hour. My graph is probably the steepest. From time 4 to time 5, it was really going pretty quickly there. And from time 5 to time 6, it was really going quickly there. Whoops, you couldn't see any of that. Sorry, didn't aim my paper to the camera. My bad. So time 0 to time 1, time 4 to time 5 to time 6. You can kind of visualize on a graph if that helps. But again, this is not super important, crucial information. If you can make sense of this, awesome. And if you can't, no big deal. Let's just take a moment then to really put it together in letter I, which I think is the part that we can all visualize. Let's sketch a graph for real. Now, you have two options for sketching this graph. I've already kind of lightly made a graph that I've been referencing for a few videos now in a row, so I can definitely copy this graph. But let's think about it. What's a graph of the function big F? We don't have a graph of big F. We never did. The only graph that we have is little f, so I definitely don't want to copy that one. But we do have some data points for big F. We have data points, lots of them in fact, that we can plot. So 0, 0, I can plot that point. 1, 2, I can plot that point. I have 2 and 5, so 2 and 3, 4, 5 here. I have 3 and 6.5, so 6, 7 would be in between. I have 4 and 4.5, so 4 and 1, 2, 3, 4.5 would be another in between. I have 5 and 2.5, so 1, 2.5, about there. I have 6 and 3, 1, 2, 3 would be up a little bit. I have 6.5 and 3.25, which I'll go back to in a second. That's a decimal. 7 and 3 would be here. And 8, 2 would be here. Now I'll go back. Between 6 and 7, I had 3.25, so just a touch above. And that looks like enough dots that I can connect. So the snowfall must have been going up, and then down, and then up, and then down. Now, to be fair, those are the precise points. When I sketched, I had a pretty rough approximation, but that does fairly effectively summarize the shape. It went up, it peaked at time 3. There's my absolute maximum. That's what I expected. Then it went down. It did hit a low point at time 5. It went back up again. I hit another relative max at 6.5. And it went back down again at time 8. Now, the absolute lowest point on the graph was at time 0. So that does still make sense as my minimum point. And now I have a visualization for what must have happened with the snowfall. The snow was definitely falling. I was watching the pile of snow get bigger. Then the snow started melting. I was watching the pile get smaller. Then the snowfall got bigger again. Then the snowfall got smaller again. That's exactly what we said on the previous page. So it does make sense in context. And if you want to flesh out the explanation, you're welcome to do that. But I don't think that is really that important right now. I think appreciating the fact that we just made this graph and made sense of it with all of the calculus is pretty big. Now that is a beast of a question. This entire playlist, all of these videos, was for one major question. And that's a lot. I'm not going to lie, that is a lot to unpack. The idea here is not that you can all of a sudden now charge right into the next section and say, okay, here we go, ready for a full analysis. This was a lot to unpack. But the reason I wanted you to see it is so you could at least start to picture and sound out how these derivatives, how these line charts, and how these first semester words can fit in a second semester context. Now that we've understood that all of the things we've ever understood about derivatives have a place here in the second semester, tied in with integrals, I hope that we'll appreciate that in this section, we're going to do our best to marry the two ideas together. All of the things that we know about derivatives married with all the things we now know about integrals and areas. It's a lot to unpack, I know. Do the best you can to think about the ideas and let them marinate, but let's call it a day on this lesson because the next section is really going to start building, and I think right now we've built plenty for now. Let that foundation settle. Let things sink in. And once we know that we've got a good foundation, we understand where all of these problems and their answers came from, then next week we'll be able to build on it some more. If you have questions about anything that I went over in these videos, pop into the next office hours or look at the answer key, talk to friends, do anything that will help. And hopefully by the time we begin next week, you'll have a fairly solid foundation that we can build upon with more examples just like this one.